In this video, we look what we think an algorithm is, what it actually is, and how we might use them to solve problems like puzzles. So let's start what we think an algorithm is. So here's definitions: a set of steps to complete a task, which sounds quite simple, and a more complex definition about making calculations, problem solving, especially by a computer. Here are examples of algorithms that people do in everyday life. So let's look about solving problems. And that means understanding the problem and understanding what you actually need. So we asked on the internet, what is the smallest algorithm? And it says a brute force algorithm is the most basic and simplest type of algorithm. And what does it mean by brute force? Well, in this example, we want to find a number. Brute force will just go through every number. So for example, in security, if there's a code, how many different options would a computer need to go through to find that number? The maximum amount of attempts would be the brute force number. Just try everything. In this example, we can see we've just got a few steps and we've got three numbers. We've got A and B, and we add them together to make C. And that's an algorithm. So that seems quite straightforward. Here's another example, what we would consider more of an algorithm with a small piece of code, and this solves the problem of checking to see if a word, like a string, is a palindrome, starts and ends in the same way. So if we go from the start to the end, or the end to the start, it will be the same. Now let's look at puzzles. How would we use algorithms to solve puzzles like a maze or the 8 puzzle? Well, here's a maze, and essentially we have choices where we go left or right. It's a 50-50 choice, and we need to make sure we do the correct one to get out of the maze. In this maze, we have 5 choices, places where we need to make the decision. And if we make the correct decision, we can go from the top to the bottom. Now, these decisions, we can model them in this example using a tree. So you can see the tree on the right, where our options go from 1 to 5, we go left, right, left to go from start to end. So we can model the problem using a data structure like a tree, and then we can solve it using an approach what we will call the algorithm. The 8 puzzle, we have a 3x3 square and there's one space. The other numbers are mixed up. Now we move the squares around, so the blank space is at the beginning, and then we have numbers 1 to 8 in this example. So how might we use a computer to solve this puzzle? Well, we can see if we look at the space, if it's in a corner, then there's 2 possible moves. In the middle, 3 moves. In the centre, 4 moves. Now if we don't move back to the previous state, we've actually got 1, 2 and 3 moves as possibilities. Again, we can use a tree to model this. So we can again use a model and an algorithm, an approach to an algorithm to solve this puzzle. So we can have a solution to a problem. But how good is that solution? Here we start looking at how we might perform an algorithm efficiently. So we might look at how we might optimize something, how we might make it the best. If that's not possible, we might need to follow a rule, which is called a heuristic approach. So to really understand this, we need to understand complexity, how simple or hard the problem is, and how efficient our solution is. What do we mean by that? Well, here we have a sequence of digits. They're either 0 or 1. And there's 80 of them. So we've got 2 options, but if we had 1 digit, there'd be 2 options, 2 digits, 4 options, 3 digits, 8 options, etc. So with 2 to the power 80, we've got a huge amount of numbers. If we made a tree, we process each node and process 10 million nodes per second. That would take 3.83 million years to process, all of the possibilities. Now we can make this problem a lot easier by splitting the numbers. We split it into 4 parts, and now we've got 2 to the power of 24 times. Now at the same processing speed, this will take 0.4 seconds. So our problem we can solve in 3.83 million years or 0.4 of a second using the same computer. So you can see that the second option is a lot better. Other examples, here we want to go from A to E. We have B, C or D options. How might we work out which is the best route? Well, if we have distance or cost, then we can use the least cost path from A to E. And we can see this when we use the graph data structure. So this is an example how we might model a network, for example, and how we might move packets around a network. Okay, if you like that video, give us a like, and we'll be releasing videos about algorithms in the next couple of weeks. So if you want to know when they're getting released, please subscribe and click that notification bell.